talk about overcoming bandwidth that looks to be a limitation of the vision on the edge today. And a little about Gidel. We are partnering with Intel and NVIDIA about the processing capabilities. We are a 30 years company focused on the high-end imaging and vision capabilities, developing hardware and design tools to support giving a customer the ability to do their own dedicated algorithms. Within that area, specifically in imaging and vision, and developing algorithms in FPGA are expertise that we have. As a product, we have the frame grabber. We have the ability to accelerate on the frame grabbers, image processing and vision algorithms. We have FPGA modules. Once the regular FPGA models are not good enough, you can start with from mid-range to very strong FPGA, and including a lot of DRAM bandwidth to associate frame applications. We have edge computers and solutions for multi-cameras from many, even more than 100 sensor and cameras to organize as a system. And as I said, development tools for the FPGA, whether we are doing it or you are doing it. And special compression algorithms that all run at more than a gigapixel per second, which is in many cases very crucial, this performance. And since not everyone knows how to deal or not have time to deal with the tailored solution, we are offering also to support customer with tailored solutions. So what is the embedded vision on the edge, and why we call it edge computing? The edge computer started from the supercomputing and the cloud application, where everything was loaded into the cloud and did the computation. And then they saw that there's more and more data generated at the edge, especially at sensors and cameras. And it is too much to send all the data to the cloud, or security-wise, you don't want to send the data to the cloud. And therefore started the edge computing. And as a buzzword, to do it at the edge. And of course, the edge computer and the embedded vision are merged together, doing the local processing, local recording, and then only reduced data or some post processing can go to the cloud. This is an example for an old slide of sensors and performance, and we already see that we had more than 10,000 frames per second with more than 100 megapixels per second, and bandwidth can go easily above 150 gigapixels per second. And there's limitation about the interfaces, and even more limitation about the PC performance and how CPU and GPU or AI engines can go along with that rising pace of sensors. So where do we have bottlenecks and limitation? We have in the camera interface, we have in the AI or CPU load, we have connection to the cloud if cloud is needed. And I'm looking here about a new type of application or non-machine vision application just to have more brighter view. And this is an example for a new technology using the AI to inspect for tumor diagnostics, rising markets with compact AI needs in agriculture, in space, and other places where compact is important. In broadcasting from stadiums and VAR and other application where you need a lot of cameras and high resolution and about 60 frames per second or 120 frames per second. And going into sports training and sports player safety, where high frame rate from 240 to 500 frames per second are needed. And in general, I think the area today, with the new capabilities of the sensors and new capability of the AI, is room for innovation. And these applications that we are looking at are sharing fast data acquisition of 10 gigabit per second, and in some cases over terabit per second, that needs to have AI or on-the-fly data reduction, recording, moving to the cloud or moving to the server to have sophisticated work. And that's the issue we are looking at. So the first thing is camera interface. And yes, USB 3 and MIPI can help in a certain limits, but the higher sensors normally will pick the 10 gigavision, the CoExpress 12 or less, and in some cases even the camera link is still active in some places. For example, in China, it's very active. And then reducing the data and processing in the cloud can be done. Local recording can be done. And the main question would be, okay, is that good enough? And what if it's not good enough? Then we can see bottlenecks in many places. We can see a bottleneck in the PCI Express or the host interface. We can see bottlenecks of the AI or GPU or CPU loads. We can see bottlenecks in connecting to the cloud. We can see bottleneck in the recording, either the storage size or the bandwidth to the storage. And what can be done to help it? So the previous lectures, we already learned that with an FPGA, you can reduce the overload of the rest of the system and doing a good heterogeneous computing. And for example, deburring, binning, and simple things like that. Then you can add real-time compression on the frame grabber and combine different flows such as the binning for immediate analyze and the compression for full data storage and reuse and so on. Here are some examples. This is a product that combines the 20 to 40 gigabit per second inputs from 10G Vision and CoExpress and another model from CameraLink, and have a frame grabber in the edge computer associated with the Jetson. And I think, unlike the TX2, the Jetson NX form factor is going to last longer. I think a device such as the Xavier NX and Xavier AGX will last longer, as well as moving from the Jetson DX to Jetson Xavier, and now to Jetson Orin. So with the computer, we're enabling a customer long life cycle by modifying inside and having the same interface out. From the previous pre-processing, we can have more than, in the basic, more than 10 gigabit per second access to the FPGA, and quite a lot of compression and other algorithms in the FPGAs. Moving into the Jetson to focus on the CPU, GPU, AI, what is needed, associate with the either a fast network going to the external in real time through the 1 gigabit after data reduction, or 5G networking, or wireless as an output interface, as well as storing of several terabytes of compressed data on the system itself. And this enables you to have a very compact, low power, and really, as the previous people said, using the FPGA performance can lower the power, and in this case can make processing of more than gigapixel per second. For example, we can take 4 co-express 12 cameras at full speed, compress them at JPEG compression, and have the computer control with the binning thumbnails, and use the storage compressing to just store the compressed data. On the higher end, we have solution going into a regular PC that can take from 10G cameras, or even 4 to 8 40G co-express into a single board, and do a full image processing over there with 300 gigabyte per second sustain rate to DRAM, and with more than 2 million logic elements. And if you put 1 to 8 such grabbers in a PC, you can handle 10 to 80 gigabit 10 gigabit cameras in a single server. So looking at kind of applications, if we're looking at drones, for example, some can carry almost nothing, and some can carry a little more. And in any case, the cooling system and real-time performance are important. And by connecting the FantoVision 20, you can take the 10G vision cameras in a solution which is compact, light, and low power. And in the FPGA, you can have the parsing of the 10G protocol with 0 frame loss, almost no power, and definitely doesn't take the ARM processing capability. And you can do some pixel correction, HDR, real-time compression, and as a whole solution, you can make hours of recording system just in that compact computer. In the tumor diagnostics, you can take 5 6P cameras, infrared cameras, and make a small modification to the version to have a customized FantoVision, and instead of 4 interface to have 5 or 6 interfaces supporting this solution to grab and send and do either locally AI or remote AI as a solution. From compression, it is very important. We've seen many customers are using 264, 265, and JPEG compression just because the data rate is so high, but they really want to have lossless compression or something like lossless compression. So in that aspect, we added the Quality Plus compression. The Quality Plus enabled to keep the SNR image quality and still have compression ratio of more than 1 to 10. And if you take a Bayer image, it's like 1 to 30 to the RGB data. This compression can go beyond the gigapixel per second, and it has really real-time compression with effectively zero latency, and it all supported by Gidel development environment. Here's an example for the sports that you can have many cameras with FPGA, compress, send, and then the CPU would be free to start initial AI and real-time feedback to the coach and the training. Here's an example for stadium where you have 30 cameras of 10G with 200 frames per second, 60 frames, 20 million pixels at 60 frames per second, and still you can grab all of them in 3 boards in a single server in the server room, and you reduce a lot of cooling issue, space, and other aspects that are lacking in the stadiums. Alternatively, you can use a 65 megapixel with co-express over fiber, and then still use a grabbing from about half a terabit per second, and still keep the SNR, record, transceiver, transmit, have a binning thumbnails for image processing and control operators, so the operator at real time can operate, decide what to see, decide what to do, and have all the data ready for these manipulations. And if you are interested in the gigapixel processing and above, and with these high-speed capabilities, you are more than welcome to talk with us, whether our solution would be good for you or you're just interesting and you have other tasks. So thank you very much for listening, and I wish you great success with your projects.